You ever stop and think about the wind? Why doesn't it just blow in a straight line? I mean, it seems like it should, right? But it turns out there are these powerful, totally invisible forces constantly at play, turning, steering, and even slowing down the air all around us. So today, we're going to pull back the curtain and find out what's really controlling the wind.
So, how are we going to tackle this? Well, here's our game plan. First, we'll look at the engine that gets the wind going. Then we'll get into the weird invisible force that steers it, learn its surprising rules, and then figure out what acts as its brakes. And to wrap it all up, we're going to use everything we've learned to bust a really common myth.
Okay, so let's start with the central mystery. We all learn in school that air flows from high pressure to low pressure. Simple enough. It's kind of like water rolling downhill. But if that's the whole story, then why do weather maps look so crazy, with winds spiraling and curving all over the globe? What's getting in the way?
To figure that out, we have to start at the very beginning. Before wind can get steered or slowed down, something has to give it that first big push. And that's where the pressure gradient force comes in. You can think of it as the starting gun for all wind.
The idea is actually pretty intuitive. Imagine a super crowded room. People naturally want to move out of that packed center and into the emptier spaces, right? Well, air does the exact same thing. An area of high pressure is crowded with air molecules, and they get pushed toward areas of low pressure, where there's just more room to breathe. That movement, that fundamental push, is wind.
All right, so if the pressure gradient is our engine, what's the steering wheel? That would be the Coriolis force. This is the absolute key to answering our big question. It doesn't actually create wind, but man, is it responsible for changing its direction.
Now, the most important word on this slide is apparent. The Coriolis force isn't a real force you can feel, like gravity. It's actually an effect that we only observe because we're all standing on a giant spinning ball. You know, if you were watching from space, the wind would be trying to go in a straight line, but the Earth is literally rotating right underneath it.
This rocket analogy makes it super clear. So, picture this. You're at the North Pole and you fire a rocket aimed straight at a city on the equator. From an outsider's view in space, that rocket travels in a perfectly straight line. But while it's flying, the Earth keeps spinning. So by the time the rocket lands, its target has moved thousands of miles to the east. From our perspective on the ground, it looks like the rocket just mysteriously curved off to the right. That apparent curve? That's the Coriolis effect in action.
And this whole thing leads to a really simple rule of thumb you can remember. Because of the way our planet spins, any moving object, whether it's wind or an ocean current, gets deflected to the right in the Northern Hemisphere and to the left in the Southern Hemisphere every time.
Now here's the cool part. This force isn't random at all. It's totally predictable. It follows a very specific set of rules that tell us exactly how it's going to mess with the wind.
Okay, here are the 4 big rules. First, it always pushes at a right angle to the wind's path, like a constant nudge from the side. Second, it's a steering force only. It can't make the wind faster or slower. Third, the faster the wind is already moving, the bigger that Coriolis nudge gets. And finally, and this is a big one, its strength is all about your latitude.
And this chart illustrates that last point perfectly. Right at the equator, there's basically zero Coriolis effect. It just doesn't exist there. That's actually why hurricanes almost never form on the equator. They need that spin to get organized. But as you move towards the poles, the effect gets stronger and stronger, hitting its absolute maximum right at the top and bottom of the world.
And believe me, this isn't just some abstract theory. During World War II, the U.S. Navy found out about this force the hard way. Gunners on battleships noticed their long-range shells were consistently missing their targets by hundreds of yards. They were aiming directly at the enemy ship, but over those huge distances, the Earth's rotation was literally curving the shells through the air. They actually had to start calculating for the Coriolis force just to hit anything.
And it doesn't just work on a massive scale. It's happening constantly, even on something as small as a baseball. A home run that travels about 330 feet is actually deflected by about 1.5 centimeters to the right. Now, that's not a lot, but hey, over that distance, it could be the difference between a game-winning home run and a foul ball. Okay, so we've got our engine, the pressure gradients, and our steering wheel, the Coriolis force. Let's bring in our final player, friction. This is the brakes of the system. It's the force that slows the wind down, especially down here near the ground where we all live.
This comparison really gets to the heart of what friction does. Way up in the atmosphere, a few kilometers up, there's pretty much nothing for the wind to run into. So friction is basically zero. The winds up there are incredibly fast and smooth. But down here on the surface, the wind has to fight its way past trees, buildings, and mountains. All that friction slows it way down, making it weaker, gustier, and more chaotic.
All right, now that we understand our three big forces, let's put our new knowledge to the test and tackle a classic myth. I'm willing to bet you've heard this one before, probably from a movie or maybe even a science teacher.
You know the story, right? If you drain a sink in Australia, the water spins one way. Do it in North America, and it spins the other way, all because of the Coriolis force. The question is that actually true? The answer is a big, fat no. It's a total myth. And the reason comes down to one thing: scale. The Coriolis force is incredibly, incredibly weak. It needs a huge system, like a hurricane that's hundreds of miles across and lasts for days, for its tiny effect to build up and organize that classic spin. A sink drain is just way too small and drains way too fast for this tiny force to have any effect at all.
The real reasons are, well, a lot more boring. The direction your sink drains is decided by the shape of the sink itself, whether it was installed perfectly level or even tiny little swirls that were already in the water when you filled it up. It has absolutely nothing to do with what hemisphere you're in. Sorry to burst that bubble.
So let's just recap the whole thing. We've got three main forces working together to create the wind we feel every day. There's the pressure gradient force, that's our engine, pushing air from high to low. We have the Coriolis force, that's our steering wheel, constantly deflecting the wind's path thanks to Earth's rotation. And finally there's friction, the brakes, slowing everything down as it drags across the planet's surface.
And there you have it. The next time you're outside and feel a gust of wind, you'll know it's not on some simple A to B journey. No, it's on a really complex trip, getting pushed, steered, and slowed down by these invisible giants. It really makes you think. The biggest forces shaping our entire world are often the ones we can't even see. What else might we be missing?